one of the common applications for the exponential functions is compound interest formulas. And here we have one of the two. It's compounding periodically. So the final amount, A, will be after a certain period of an investment, after time t, t is going to be in years. P will be the principal or the initial investment. And N, you see twice in the formula, is the number of compounding periods per year. Okay, the other compound interest formula is for compounding continuously. And it's a little simpler. A is equal to the principal. E, that's our constant, approximately 2.718. You recall we've used that in exponential functions before. And then the exponent is going to be simply R times T, where R is the quoted interest rate, and T is the number of years. I meant to say over here, R has to be in decimal. It's usually given in percent, and we convert it to decimal to put it into the formula. So let's think about N, of course, is another issue when we're working with compounding over certain periods. N would be equal to, say, 1 if we're compounding annually. If we're compounding monthly, N would be 12. Another one would be N equal to, say, 4 if we're compounding quarterly. Okay, so let's do an example where we're going to invest $700. That's going to be our principal, and we're going to invest it at a rate of 6%, compounded daily. And we want to know how much we will have at the end of 2 years. So we want to find A of 2. So after 2 years. So A of 2 then is equal to the principal that we invest, $700. 1 plus R 0.06 divided by daily. We're going to use N equal to 365 or 365 days in the year. And then NT will be 365 compounding period and 2 years. So we just plug all this into our calculator and we come out with an approximate final amount, which is of course over $700. We'll have $789.24 in our investment after 2 years. Another example might be a present value problem where we're asked to find how much do we invest in order to accomplish an amount of $25,000. So we want $25,000 at the end of 10 years. We have an opportunity to invest at 7%, and this time compounded continuously. So we have no compounding periods. We'll use the formula A of T is equal to P, the principal, E times RT. So $25,000 is our final amount that we would like to come up with. We don't know what to invest. That's our unknown P. E, the rate is 0.07. And we want this after 10 years, so T is 10. So to solve for P, we simply divide both sides by our exponential term over there, or factor. So we'll have $25,000 divided by E. And when you multiply 10 times 0.07, you just get an exponent of 0.7. Plug this in my calculator, and I come out with a principal, or original amount of $12,414.63. So this is what we need to invest, or our present value. That we need to invest at this point in order to have $25,000 at the end of 10 years. And again, we're using the compounding continuously formula in that particular problem. We have another type of problem that would ask us how long it's going to take to double our money. And we're going to use, again, the compounding formula here. Let's put that over here. And we'll write down the question. We have an opportunity to invest at 5%, and this will be compounded monthly. We want to know how long will it take to double our money. Okay, so we're solving for T. Again, we're going to use this formula where we're compounding monthly. So the amount that we want to end up with is twice the original investment. So I can simply put in for A 2P. And that's going to be P times 1 plus R is 0.05. Now N is monthly, so we'll have 12 compounding periods per year. And NT, the exponent will be 12 times the unknown, which is T. Well, if we're going to solve for T, the first thing I would do is divide through by P. Okay. And then I'm going to take the log of both sides. You can use the common logs or the natural log. I'll use the natural log here. The natural log of 2 is going to be equal to the natural log of 1 plus 0.05 divided by 12. And we have an exponent of 12 times T. Now the properties of exponents or logarithms say that the exponent on the argument can come out front and be a coefficient. So now I have the natural log of 2 equal to 12 t times the natural log of 1 plus 0.05 over 12. And the last step then would be to divide both sides by this coefficient part of the t. So t will be equal to the natural log of 2 divided by 12 times the natural log of 1 plus 0.05 over 12. Okay, and this can go straight in the calculator just like that. The one thing that you want to be sure that you take care of in the calculator is to put parentheses around your numerator and around the total denominator, because you have several factors in the denominator and the calculator needs to know exactly all those factors are in the denominator. So then the calculator will give me an approximation in decimal. Turns out to be 13.9 years. And so it's going to take 13.9 years to double whatever investment I make at this particular 5% rate compounded monthly. Another type of problem we might have would be to compare different interest rates at different compounding periods over a given amount of time. And in order to compare those, we put in $1 for T and 1 year for the length of $1 for P and 1 year for T. So here is my quandary. I have an offer of 6% compounded monthly. And another investment opportunity is offering 6.25% compounded annually. Now, in order to compare which one might be the best investment, I'm going to find what's called the effective rate. For each one of those opportunities. So again, in both of these opportunities, I'm going to let T equal to 1 year. And I'm going to use P, the principal, as $1. And see what kind of interest I get in 1 year. So the first investment is at 6%. So we'll come up with A equal $1, 1 plus 0.06. And we're compounding monthly, so we would use 12. And NT is going to be 12 times 1 year. Okay. Well, I, again, plug that in my calculator, and I come out with a little more than $1, $1 and a little more than 6 cents. Okay. So I've earned a little more than 6 cents here. Now, I can subtract off the original amount that I invested, which is $1, and I can convert that then to the effective interest rate. So my effective rate for this investment is, again, subtract the $1 off, and we have 0.061678, or in percentage, it would be 6.1678%. So that's the effective rate in that investment. The other opportunity we have is 6.25. So again, A is the principal, which we're going to call $1. 1 plus 0.0625 and it's compounded annually, so that would just be a one time a year. And N is 1, and T is 1. So we do the calculation here, we get a final amount of $1.06 plus a little bit more. Again, subtract off the original investment, and we end up with a little over 6 cents. And that is in percentages 6.25% as the effective rate. So comparing those two effective rates, it appears that the second investment is going to be slightly better than the first investment, 6.1678% versus 6.25%. So if I were choosing to, between those two investments, I would definitely go with the second investment. It's going to give me a little bit better return. One more type of problem that we might run across is to find an interest rate. We've solved for A, we've solved for P, and we've solved for T. Now let's find what R would be for a particular goal. So we want to find the rate if we are going to be compounding annually once again. And we want to triple our investment. In 10 years. Okay, so again, we're using this formula because we're working with an annual compounding period. So the triple amount of what we start with would be 3 times the principal is equal to the principal, 1 plus. Now we're going to find R. So R over N, which in this case is 1 because we're compounding once a year. And NT would be 1 compounding period times 10 years. Okay. And we're solving for R this time. You can divide by P and get rid of that variable. And now we have 3 is equal to 1 plus R to the 10th power. And solving for R, I want to take the 1/10 power of both sides. So we're raising both sides to the 1/10 power. Okay, so on the left I'll have 3 to the 1/10 power. And on the right I'll just have 1 plus R. 1/10 times 10 is 1. Subtract 1 from both sides. And we have the value for R. I can plug that into my calculator using the exponent caret button to get the 3 to the 1/10. And it turns out that R is going to be 0.11612, or as a percent interest, it would be 11.612%. So if we invest our money at 11.612% compounded annually for 10 years, we will have triple the amount that we started with.